Okay, so welcome everyone for one more section, quantum hardware course, like quantum optical models. So today I will continue and we will finish the part of the coherent states. Okay, my idea today is to give you guys some properties that we just discussed the last time, but try to show mathematically. So okay, so I'll try today to have a shorter lecture because last time I think was too big. So let's start. I will share. Okay, so I believe you guys are seeing my screen and see these slides. So I will just give a summary from the last lecture because it was a lot of information. And then we'll see some properties about coherent states, and in the next Friday we will apply for quantum computation. So let's start again today. Okay, so this is the second part about the coherent states. We'll see some properties of this very important quantum, or sometimes called semi-classical uh, states. So let's start reviewing some of the formalism we studied in the previous lectures, especially in the last one. As a typo here, laser. Laser light is a coherent electromagnetic wave. That's the type of laser light we are using. With these coherent states or electromagnetic waves that we are considering is the closest possible analog to a classical electromagnetic wave. So we have let's say a quantum state, and then this coherent state that we are consider, how was defined in the last lecture, is the closest possible to a quantum state, the closest possible to a classical, what we could call a classical state. And it has several advantage because this is one of them is easiest to make experimentally, because we know how to deal with the classical waves. So if you have a quantum, but it's the closest possible to a classical, so it's the easiest of the quantum possibility. All the quantum possibilities, this type is the easiest possible. So in the last lecture, we discussed quantum states that describe this type of ideal laser light, that is the coherent states. And since laser light has a well-defined amplitude, we have defined coherent states as the eigenstates of the amplitude operator. Remember that when we expand the classical electromagnetic field in terms of the different modes, series of modes, we quantize this field using considering the amplitude for the classical fields, and we relate it with the annihilator operator of oscillator. And that's why sometimes you guys can find in some books instead calling annihilation operator, call this amplitude operator because of this relation. And we define in the coherent state, that is we call alpha. In fact, we show that A applied to alpha is just alpha is the eigenstates of the ket alpha, the eigenvalue, sorry, for the ket alpha is given also by the same letter alpha. And because the annihilation operator A is not a Hermitian, the eigenvalues of A are complex. So this guy here, in general, are complex, the alpha. And we note that the annihilation operator acts on the state alpha with no annihilation. Okay, since this state is by definition it's eigenvalue, huh? Like this this expression here. So the annihilation operator, this A here, it annihilates the number state. Sometimes it's called Fock state, that we saw in the lectures about the harmonic oscillator. But in this state, the coherent state, in fact, it annihilates nothing. It's given this way, and this is it's like it's not so uncommon, because this type of property suggests that might exist other type of states where the annihilation operator can act with no annihilation and sometimes even create. It happens sometimes in thermal states as well, so it doesn't annihilate as well. So this name is because of the definition when we use in the case of the Fock state, or the N state that we call when we was like studying the harmonic oscillator. So okay, so in fact it was shown that the operator A acts as an annihilator in the states that sometimes we call subpoissonian, as the N states, that's the Fock states, and a creator in super Poissonian states, like the thermal states and phase states and other ones. But we will not show details about this today. We today we will just show like that this third part, that when they are considered doesn't not create or annihilate anything, is in Poissonian states, like the coherent states, and we'll show this today, that this this Poissonian behavior related with the coherent states. And to study coherent states more carefully, just try to remember the last lecture, we introduced the displacement operator given, that was defined by this expression, which is unitary. And this operator displays, it has his name because we like show that in fact it displays the amplitude A by a complex number. So in some sense, I should have put here, but it displays the vacuum, the vacuum state in the n states, right? When n equal to 0, so we have a displacement. So in terms of the n states, that sometimes is called Fock states, the state alpha can be written this way. So we stopped last lecture with an expression like this, that when we are using the Nielsen-Schoen book, it starts with this expression. He doesn't explain well from where this expression comes. So that's why I decided, like, before following the Nielsen-Schoen books, so we study a little bit some properties of these states. And in the case of the single harmonic oscillator, this N refers to the energy level, while in the case that we are considering here in the electromagnetic field, N refers to the number of photons that we are considering, which are also related with the energy level of the system. So this is just a brief summary that maybe in the last lecture was maybe too fast. We were talking, but today the idea is to study some properties, some consequences of this material.
If I could interrupt a
Yes.
second, those last two slides, it would be great to have a copy of them. They're kind of the Rosetta Stone for decoding the notes from last week.
The last two from the last week.
The, the,
We
the, the last two slides you just showed explaining
Oh,
the
okay.
alpha, the A, and particularly D, because when I was then going through my notes, I couldn't keep track of what A and alpha and D were. So this
Mm,
is very helpful. It would be nice to have this.
yes, yes, but we are also like uh, in the GitHub file. We are letting my notes available. I don't know
Okay,
if it's
I
updated. So all the things that
okay, yeah.
I did in the and in general, I put these slides together. Like, let me show you. So,
Okay, thank you. Last I
so
checked, the GitHub wasn't updated, but
oh,
maybe
okay.
that's
So
happened
maybe
since.
okay. So these slides are when I update every time I put here in this when I'm doing the whiteboard. Let me.
Okay, yeah. Thank you. Yeah, I
Okay,
got
okay.
a little lost reviewing my notes without having the key of what alpha and D were. Now it's actually much clearer to me. Thank you.
Oh, okay, okay. But I mean, these slides when I put here are exactly the same when I show because I tried to put everything in the same file, but I'll say like to update the GitHub with the new files. So okay. So here in the last lecture we stopped. Let me put here. We stop in this expression. With this expression. Alpha exponential alpha square sum alpha to the n factorial n. So the ratio of the coherent states with the n state number state n. So and I call this expression 716 in the Nielsen triangle. And I think I will put in the end the reference because sometimes it's just the notes are not enough because these all these things that we are discussing here we don't have in the Nielsen Schwing book. So I'm using basically this book here, and I will put the reference in the end. Okay, when I finish, I will write the reference of this book, Quantum Optics, where I'm discussing the this part of the this to read as a material to read. So okay, so we finish here with this expression, and we studied about some properties, coherent state properties. Okay, so the first one I'll call here, okay. So it's related to the number of particles. So not that. And I can apply the number operator n to alpha to this state. And if you remind the definition, n is just a dagger, a alpha. And if you applied a to alpha, we saw in the last time that a applied to alpha is just a dagger. Let's this is just alpha. Okay, this is a complex number, as we said before. So this alpha can come here, a dagger alpha. This will give us just alpha square, modulus square. Okay, this is alpha. Okay. Okay, then we can see the average. So alpha and alpha, this will be just like when we applied here alpha, the bra alpha here, this will give alpha square alpha. And this is the identity, right? This is the identity. So I'll call this just alpha. So the number of particles is proportional to alpha square, modulus square. So this is one of the properties. Another is, we comment before, is the probability of finding n photons in the state alpha is given with. So the probability you call here P of find any photons. The probability, if we define, remember from the review of quantum mechanics, is just this, and represent in this way, which is the n alpha square. Okay, but we know who alpha is in the first expression. So P of n will be simple exponential minus alpha square, the sum n equal to 0 to infinity alpha to the n over n. Delta. Now, let's see here. I think my notes are wrong because there's a square root here. We don't have this square root. So this is just n factorial. Okay, in this here it will be n. Okay, which is a delta n, and this will give exponential minus alpha square alpha to the n over n. Okay, which is a Poissonian distribution. Which is Poisson distribution. Okay, so we can see, I'll try to draw something here. We can see like this probability in terms of the, let's change the color. P of n by n. So we can see, let's say, if we choose like an alpha square in the order of 0.1, we can like easily calculate this expression. And we can see that in terms of n, is will have like a peak close to the value of alpha. So we have a plot, will be something like this. I'll change the color. So I'll use more than one. So this green will give me something like u1, 2, here is 0, n equal to 0, n equal to 1, 2 is 10. We'll try these values. So he will give me, this will give me a peak here, and it comes to 0. Okay, something around here. It's not exactly actual, something like this. The thing is, the peak, the maximum value is here, close to 0.1. So this, you guys can just put the numbers here, you'll find something like this. Yeah. Okay, and another value, let's say alpha equal to 1. So we will have the two maximum values when n equal to 0 and when n equal to 1. You can see that for both values, this will give me something like this. So to 0 and to 1, these two values, they are the same. And then it goes down. Like exponential, okay? It's not the... And the other value, maybe more interesting, let's go alpha squared. When alpha is becoming bigger and bigger, this will have something more like a Gaussian shape, meaning where the peak is the number of particles. The number of particles, the maximum number of n associated with alpha squared. So we'll have something like this. The maximum is around 10 when n is equal to alpha squared. This is because what we found here, the average, the number of particles is equal to alpha squared, right? So the maximum, in fact, we could write this in here as the exponential of n. n okay, so we can see that for alpha smaller than 1, p of n, the probability, x maximum at n close to 0, n equal to 0. And for alpha squared bigger than 1, p of n, like in this case, in the red case, p of n has a peak at n equal to alpha squared. In fact, it's not exactly, but it's close. Peak close to n equal to alpha squared. Okay. So another property that's called C, as we discussed earlier, that the coherent state is the state of minimum uncertainty. But we just said that. Let's prove this now. So, as discussed earlier, the coherent state is a minimum uncertainty state. So, okay. To demonstrate this statement, Let's use the coordinate representation of the oscillator. Oscillator number state. Oscillator number state. So the coordinate representation on the psi and of R, just to remember, defined this way in quantum mechanics. And now you need to just to remember the things we did in the past. So I will put here things that we already studied. So this was defined in the quantum mechanics. You can see this in the coin book, coin energy book. And it follows from, I'll put here when the things that we proved before. So if you see the notes from the lecture 7, and the noted is in the page 3. So okay, the notes that are in the GitHub. So if it's not update, I will ask to download it to update in this weekend. In the lecture 3, we prove we in fact we define this. A was defined this way. This is the lecture 7, page 3. Sorry. 2m omega h bar m omega x plus IP. Okay, but here for some reason isn't. Well, I'm using the letter R instead of X. It makes no difference. So just what you have in the notes associated with the lecture 7, we use X there, but today I was using R. So, but it does change nothing. Okay, so this was defined before in lecture 7, and we also show just a review using the fact that P is minus IH bar D R. We saw this in, I'll put here, lecture 6, page 13. So, okay, in the notes, we can find page 13, the notes associated with lecture 6. So using the fact that P is this, and from lecture 8, page 4, we have this equation. We saw that the Schrödinger equation could be written in this way. DDR psi 0 r equal to 0. And the solution we found in this lecture 8, page 4, the psi 0, this n equal to 0, okay, of R is 1 over pi R0 exponential R square R whole square. And this R0 we define this constant. Okay. And the general solution, this is for psi for n equal to 0, and for the general psi of min, we found this. In fact, 1 R0 to the n, and this minus R0 ddr to the n psi 0, where psi 0 is this guy. Okay, so this is the fall, is basically the lecture 8, but it's page 5. You can review these things, okay? Okay, and we can use, I'll let this part here as a homework. It's easy. It can be verified. That these wave functions satisfies the orthonormality condition. Which is this psi n of R psi m is delta n. Okay, but this I'll let as a homework. In fact, to be simple, you guys can just use, because this in this lecture I stop in a representation like this, but in fact this could be simplified, this expression here, using Hermitian polynomials. So psi n of R, this guy here, could be written to n and psi 0, where this h of n are Hermitian polynomials. And this would be simple to show this, because you'll just need to use some properties of these polynomials that you can find like in tables, if you don't want to demonstrate. So, okay, just a review, and also, if if we want to prove like the minimum uncertainty. So we need to see the variance, the expectation value in the momentum and position. So the expectation values in the momentum and position are. So in the momentum is just delta p square is the expectation, the variance in p square minus p, the variance of p square. And the same for r square. So, okay, but we saw we can evaluate this in lecture. Let's use equations from lecture 8, the notes, the page 3. So we found this in the end state R is equal to this 2m omega. This will give us n delta n minus 1 plus n plus 1 delta n plus 1. Well, using the properties of the delta function, so this will be always 0. Okay? Because the same n at the average in the same n. So this is 0. And the same for p. The same for p. For the momentum, we found this m h bar omega over 2 n plus 1 delta n plus 1 minus square root of n delta n minus 1. It's the same, 0, 0. So this second term here in both are 0. So, okay, so we need to find this, the p square and the r square, and then take the expectation value. So from the definition of R, I think I put here, but lecture 8, page 3, you can find R squared is just h bar to m omega multiplied by a dagger square plus a dagger a plus a dagger. So, okay, I need this guy here. And this is the average in the end state, like this. So you need to evaluate these 4 terms. So let's see, it's simple. Can do it in one line. A square, we need to use these properties here. I'll put here. So we need to use that a to the n is this, n minus 1, and a dagger to the n plus 1, n plus 1. So a square and this will be simple. Right, if you use these properties here, okay, I'll just put the answer. This will give I something n minus 1, and something like n minus 2. In fact, this is 0. Okay. This is 0, it's easy to check. Let's just use these properties here. This first is 0. The second is also 0. The second term is a dagger squared to the n. And the others, this a dagger a to the n will give us n, and this n a dagger to the n give us n plus 1. Okay, let's see very quick here. These terms will be 0, okay, because this will apply twice. The n state, the annihilator, so we will have one, the bra will be n, and the other bra will be n minus 2. Okay, so this is 0, this is 0, this is 0 as well, because it's n, the bra, and the cat will be n plus 2. So we will have 0. And here we have we will annihilate once, so we use this, we'll have n minus 1, and then we'll like create. So n minus 1 plus 1 will be n. So we'll have n on one side, and the bra will be n, and the cat will be n too. So this will be, in the end, this will be something like this. This term. And the same here. So this is n, and this also is n, which is n. Okay, because this will create, so we have n minus plus 1, and then we annihilate, so we'll have n and n again. And the constants you can check, that will, in this case will be n, and in this case will be n plus 1. So we need like to just use this 4 guys here. So we'll have that n r square n will be just h bar sub 2n omega 2n plus 1, because this one n, this n plus this n plus 1, so it's 2n plus 1, which is the same h bar and omega n plus 1/2. Okay, so it's simple to verify this. Just use these properties. And the same for P and P squared n. We'll find that n P squared n. We use the definition of P. I didn't put here, but we in the same. We can see this in the same lecture. I think the same page. If it's not the same page, is one page after we define P. So P squared will have only h bar omega m and plus 1/2. So we'll do the same manipulation here, and we'll find the P squared. So the uncertainties in the generalized momentum and coordinates variables are given by. So delta P is defined this way: P squared minus P. This we saw as 0, and this guy here is this h bar omega m and plus 1/2. And delta R, this square. R minus this guy, which is 0, and this other, we just slow this. The expectation value for the momentum and the position is given by this. And the uncertainty product is delta P, delta R. So delta P is the square root of h bar omega m, and the square root of this 1/2. This is delta P, and delta R is this h bar omega square root of this. And in the end, delta P, delta R, this guy goes like this. So this h bar n plus 1/2. And the minimum possible value, now for n equal to 0, which is the vacuum state, for n equal to 0, we have delta P, delta R, bar over 2. Which is the minimum possible value allowed by the uncertainty principle, right? So this state is the minimum state of uncertainty. That's why that always the closest of the quantum states, this is the closest possible for a classical field, classical state. So this is the most classical of the quantum states. The advantage is that it's easier to carry out experimentally. Okay. So we had just mentioned this in the last lecture, and now we see. So okay, another property is called D. Is to see if the coherent state is in fact a complete set of states. So we know that the position momentum states, as well as the Fock states, they are. So let's see this very quick about the coherent. So this set of all coherent states is a complete set. Complete set. So to show this, let's consider the integral. So to show this, if this is complete or not, let's see the integral this way. So I will use here the expression we found about the coherent states in terms of the Fock states, the number states. So this will be something exponential alpha square over 2, this sum alpha to the n times delta to the bracket alpha minus alpha square over 2 is 2 sum infinity that go in prime alpha conjugate in prime. Oh, sorry, the bra. Okay, I want this relation. Okay, so the integral is in alpha. So this will have just the double sum outside. The states. The integral. This 2 alpha exponential this alpha square alpha conjugate n prime alpha n. So okay, and the things just to solve this integral, I'll not show here. I'll just give the result. Okay, this integral I'll call int. So int is just something this pi n factorial delta n. And just a hint, you can use define alpha as alpha exponential I theta. Okay, and make like you could like write this like int as the integral of this the alpha exponential, and then we use some tables and you find this is not the theta. Okay, just a hint, but this is the result of this integral. Okay. And then, so this guy here, the beginning, we will find that this is the sum n prime n and n square root of n prime pi n factorial. That's the integral that we delta. Okay, and then using delta function property, we will find that this is pi sum of n over n factorial, which is just pi sum of n. And this is the identity. Okay, identity. So the result here is pi. And then, in fact, when we using the fact that these eigenfunctions are complete, the relation is 1 over pi, because there is the identity here. Alpha d of alpha. This is equal to the identity. Okay, integral minus the plus infinite. Okay, and this is in opposition. This is the completeness relation. So this this is the complete relation for the coherent state. States. So we see that this base is continuous because the integral relation. The base is continuous, and sometimes called overcomplete. Basically because of this presence of this pi here. If we remember, this is in opposition to the Fock states or number states. Fock states, that's the completeness relation, is discrete and complete. Is equal to the identity. Okay, discrete and complete. And also to the set in the position and momentum we have something that is continuous. X is continuous. This is the identity. The complete, continuous, and complete. And the same in the momentum, right? In the P entity, also continuous and complete. Okay, in the case of the coherent states, it has this property that sometimes is called overcomplete, because it's proportional. If you want to use this relation, a relation of this, you need to divide by p or by pi. So okay. And another important thing that's is related to this is that they are not orthonormal. So the coherent states corresponding to different eigenvalues alpha and alpha prime are not orthogonal. Okay, you can see this alpha prime. We can use like the definition the first expression we use today. So this will be something like this. The square minus alpha prime square over 2 and the sum, double sum. Again, alpha prime conjugate, alpha prime. And here is a delta function, delta of n, so one of the sum goes away. And we can show that this is simple exponential minus alpha square over 2 minus alpha prime square over 2 and this sum. So because of the using the properties of the delta function, one of the sum goes out. We have only one over n. Oh, I forgot here the n factorial. We have n factorial here because the in the first expression we saw today. So this is just if you use like the definition of exponential function, we can write this as exponential minus alpha square over 2 minus alpha prime square over 2. And this is the exponential of alpha prime alpha star. So this is just alpha square over 2 minus alpha prime plus alpha prime alpha star. Okay, and this is not a delta function. This is not orthogonal. Okay, so I think this today, as I told you, would be shorter. These are the main thing. Okay, so I just forgot. Yeah, so this is different of a delta. This is not a delta. And but we have that this. If you use this, it takes the modulus square of this guy here, we can show that this is just this guy. A square. Okay, which is a Gaussian that goes to 0 when it goes to 0 only when goes to 0 only when alpha and alpha prime differs significantly. And they go to infinity, right? Very big distance. Okay, so guys, it's just to see some properties, important properties from this. Okay. And I'll put the reference notes I told you, the book I told you. From this, on the lecture from today, reference, and in the last lecture about coherent states is this quantum optics. M.O. Scully. So, Scully and M.S. Zuberry. This is the chapter 2. Let's just check this. Yeah. Not everything from, I think from page 50. Page 50 to 55. Okay, it says, I think this is the main properties. The book is this one. I showed you at the beginning. So you guys can find some more discussions. I think it's good to have a read. So, okay. So I think it's enough today. I will stop recording. Otherwise, the video will be too big. Okay. Okay, so just to remind, next Thursday, the 16th, we will have quantum team, the quantum team roundtable, and the next Friday we return to the quantum hardware course. Then I will talk more about quantum computation. So, okay, just stop recording. See you guys from YouTube.
Thank you, Carl.